We're now going to look at some of the difference that different clustered indexes can make to a non-clustered index. So this is kind of, well, it is definitely, this is extending on the same topic we talked about in the previous module, but in addition, we're also going to talk about windowing for, we're going to talk about windowing for indexing functions. I was going to say, we're going to talk about indexing for windowing functions is the actual thing that we're going to talk about as well. So we continue journeying on around the world of disk-based row store indexes, and we encounter index Doge, a meme so old, but I just can't stop using it. So we've got a new index question, and the question is about two different tables. So let's say that Doge is considering, Doge is a DBA, of course, Doge is a DBA, or a developer, it actually doesn't matter, but Doge is testing a clustered index change. And these two tables are identical, except on this table, we have an ID column, which is a big int column, which is being added and tested out as a new surrogate key. So a big int column has been added to the table on the right, 8 bytes per row. And on this, the old table, we have the same 3-column clustered index that we're used to working with on ag.firstnameByYear. Now, ag.firstnameByYear, this table, by the way, is a little different than the tables we've been working on. ag.firstnameByYear before did not have all of these columns, which are named garbagey names like report column 1, report column 2. These have been added to this because in the real world, when we work with tables, a lot of times the tables don't just have 4 or 5 columns in them. The tables have lots and lots of columns in them. So in your database, you have these tables already created for you, and they've been mimicked up to behave like a wide table in the real world. And we do have different data types spread about here. Some are bits, some are numeric, some are dates. These aren't all variable character columns, but there's some of those in there too, right? So just tried to make it as messy as a lot of life often is. So we are changing the clustered index, and we've got a very important query. Now, unfortunately, our very important query uses a bunch of those garbagey columns, but here's a little bit about what it does. The query it has a CTE at the top named nameRank, and nameRank is looking at this one's looking at ag.firstnameByYear natural. This is the old original table. And it's using a row number windowing function inside the nameRank CTE to rank the names based on the report year and the gender ordered by name count descending. So the names for a given report year and gender with the highest name counts will be ranked number 1, right? So if the most popular name for that year and gender combo will be ranked number 1. And then at the bottom of our query, we are saying, okay, we want all the rows from nameRank that are the number 1 rank for that report year and gender column. And we also want to join back and get all of those garbagey report year columns from it too. We are also joining to ref.firstname to decode the name and not just return the ID, but to also return the name itself, because this is our table that actually is normalized. This isn't our garbagey table that's both normalized and denormalized. We don't actually have first name in this table. We just have first name ID. So the question here is, how do we index for this and make it work? Now, we already have an index for this on the table, and we are using the same index definition on the new table. Our index says we are going to index on report year, gender, and then name count descending. The way that our query is written in our windowing function, it is partitioning by report year, it is partitioning by gender. So for every report year and gender combo, we are getting the row number based on name count descending. So those are the 3 keys in our index, and we even have the descending matching it. So that's both on the old table as well as the new table. Sounds great, right? The index was created for the windowing function, right? Here's our 2 partition by columns, and then our order by column are in the indexing keys. So the question here is, what is Doge missing? What could go wrong? Is that index, and let me switch on over to Management Studio to try to get everything onto the screen here. It's going to be tricky with this query here, but we can do it, I think. So looking at this query, and actually you only really need to look at the first index definition. This is really a spot the error problem. This index that is designed for the windowing function. The question here really is this well designed for the query? And is it likely to still work if we change the clustering key? Or is there something that is missing from this index? Hopefully you can do it without having to add in all of the report columns. Is there something that is missing from this non-clustered index that if we go change the clustering key may go away and cause a performance problem? Now, one approach to this is to think about what the clustering key is on the table, but another simpler approach to this is simply to look at what's happening in the query and what's happening in the index and say, if I was indexing for this query, is there something I think this needs, ideally without adding every single report column in the index? So see if you can spot the problem. I am going to, and the reason I like to do this one, that is not the right file, that was just a random SQL file. The reason I like to do this one is in the real world, we do often have to try and spot the problem a lot, and it's really kind of hard. So getting a little bit of practice for it can help. So I'm going to do a 4-minute timer on this one. See if you can spot the problem. Is there something that this index needs? And if so, what is it? And where would you add it to the index to help the query out? So I will be back in approximately 3 minutes and 43 seconds. All right, let's switch on back to Slack. Any ideas about how this index may be missing something important for the windowing function and the queries here? All right, let's take a look at this. So I'm going to go ahead and switch on over to the solution file here. And I'm going to make sure, let's use the correct database. I'm going to make sure that I actually create both of those non-clustered indexes there. So what I've got is I've got the, oh, and I think I actually don't have things turned on there. There we go. So what I've got is I've got the, let me make sure I'm still sharing properly. There we go. So I've created the index both on the table that has the clustering key on report year, first name, ID, and gender, and on the table named surrogate that has the key on a new column, which is named, what is our new column named? Our new column is named just ID, and it's a big end. So let's compare the performance of these between the two tables. And this is kind of, this is an example of, if I just change the clustering key, what problem might sneak up on me. Now, there is one problem with my new table that we should think about, by the way, before we even tune things. And by the way, this does impact performance. My new table, if I am ever changing a key between two tables, and my old table had, let's actually refresh this here and look at the keys. Wait a second, ag.first name by year wide natural, hang on, what do I, let's take a look here at what I've got. Oh, okay, I have a, so nothing shows up in the keys because what I have here is a clustered index, not a clustered primary key. If I script my clustered index to a new query window, it does show that it is a unique clustered index. Arguably, this should have been a clustered primary key, but sometimes you'll just find that someone did it as a unique clustered index. Making it a clustered primary key really denotes a business rule about the index, right? So this was done as a unique clustered index. On the new table, if I'm not enforcing uniqueness against these three columns, well, a couple different things can go wrong. We could actually get invalid data in there. We could get duplicates that weren't allowed on the table before, but it also can change our query plans. The uniqueness of rows can actually change and impact the performance of the queries. So on the new table, if I am changing the clustered index, and that has already been done on the new table already has a unique clustered index on ID, I probably want to enforce uniqueness using a non-clustered primary key on the columns that did used to have uniqueness enforced by the old clustered index, right? So this is a non-clustered primary key does create a non-clustered index in the background, right? So a clustered primary key is the table itself, enforces uniqueness on the key or key columns. A non-clustered primary key is a non-clustered index that enforces uniqueness on the column or columns specified in that. It is technically a constraint, but it is backed by an index. So I'm going to go ahead and create that, which will enforce uniqueness on those columns. So let's go ahead and test the query. So this table has now, both tables have identical non-clustered indexes, and my new table has a non-clustered primary key to kind of at least let SQL Server know, hey, this combo of things has to be unique. Let's compare the queries. So this first query is going against the old table that has unique clustered index on report year, first name ID, and gender. And I'm going to just shrink both of this one goes against the new table. The tables are referenced twice in both queries. So let's go ahead and baseline these and see how they perform. So on the old table, our windowing function is fast and it already has returned information. You can see the wonderful data that I have in these columns here. It's fantastic, isn't it? But it's slower against the new table for sure. It's actually still going. So it took 3.4 seconds of CPU time against the old table. Against the new one, it took 10 seconds of CPU time. On the old table, we were doing 390,000 logical reads. On the new one, we are doing 771,000 logical reads. Let's go ahead and turn on our execution plans and compare them. So we're going to do it one by one. The first one here, we're going against the old table and looking at our execution plan here. I think I actually, wait a second. Yeah, this is the old table. Let's run that again. That was slower than I expected. Let's look at the results again. 7 seconds. So this one is going against the first name by year wide natural, both places. I want to turn statistics.io on as well. I think I'm just misremembering. So CPU time was, okay, so what I did here, this is a fun, come on. So what I did here with a CTE, it actually cares. It's one of the few statements in SQL Server that cares that the preceding statement was properly terminated by a semicolon, and I failed to do that at the end of my set statistics.io and time on. So it threw an error that I hadn't properly terminated before the CTE, which is always fun. Oh, I do, now I have, hang on. Okay, I'm gonna highlight one query. There we go. I'm getting a little excited about what's going on. There we go. That's the new table. We're gonna scroll up. We're gonna turn on statistics.io and time. There we go. All right, okay. So CPU time around 3 seconds, elapsed time 3.8 seconds. I was getting a longer runtime where I was seeing 6 seconds there, and it could be, this is part of why I like having this on to be able to measure it here. We do still have the 390,000 logical reads. This is a VM that's just running on my laptop. Periodically, I will just have the cores be busy on my laptop and it will cause delays in the VM. So seeing consistent runtimes is something that is useful. And when I see an inconsistent runtime, I usually want to check if that's the issue or if it's something else. So I'm not entirely sure what it was. I think it may have been that, I mean, the fans were on my host, so I think it may have been my Mac hypervisor host doing stuff in the background. All right, in any case, The non-clustered index on the old table appears to be working pretty well. We have an index scan on the non-clustered index. We have a segment operator. What is the segment operator doing? We're working with windowing functions, and segment, I like to make fun sometimes of the descriptions in here. Segment does not have a description, right? Segment is just segment. It's segmenting things up, right? We can see though, if we dig into the segment operator, see how there's a group by here. So segment, what is segment doing? We are grouping by the partition by column. So in our windowing function, we're doing the row number, and then we're partitioning by 1 is row year, 2 is gender. So this top row is the list of them both, report year and gender. So what the segment is doing is handling the partition by in our windowing function, where we're saying, okay, we want to partition by report year and gender. If we look at the output list of the segment operator, it is outputting report year, gender. Hey, wait a second. It's outputting first name ID and name count. Okay, hang on. Let's go back and look. This is a clue. This is an important clue. When we are looking at our windowing function and we're indexing for a windowing function, we need to index for our partition by columns. That's report year and gender. We need to index for our order by columns. That's name count. There's something else that it's actually working with here, though. When we look at our output list, it also cares about first name ID. Why does it care about first name ID? It cares about first name ID because when we are joining from the windowing function back to the other table down here, first name ID is part of the join criteria, and it also is what we are joining on to ref.firstname. When we're indexing for this query, we don't necessarily have to cover everything in the query, like all of these report columns. But when it comes to the windowing function, we want to, you can't just look only in the windowing function itself. You do want to look in the windowing function and be like, okay, I should index for my partition by columns. I should look at my order by. You also need to look at what other columns is the query using to do things like limit what's coming out of here or join the results of the windowing function to other things. And that, I mean, we have covered all of the join columns so far, gender and report year. The one we haven't covered is first name ID. That is not in our index definition here. It is showing up in this query because it's in the old table named natural. The clustered index key is report year, first name ID, and gender. So it got snuck in here based on having to add the clustered index to all the non-clustered indexes. And it's being useful here because it's being passed along here. And then if we look at this hash match probe, it is for this hash match is a join hash match. It's not a hash match aggregate, it's a hash match join. And if we want to know, hey, what are you joining on? We can look for the hash keys probe. It is joining on first name ID, gender, and report year, just like we see in the T-SQL. So part of the magic that's making this index work is that first name ID, the join column, is secretly in that non-clustered index. If I run the same query against the new table that has this same non-clustered index, but there's a different clustering key on there, the clustering key is now just an ID column. It doesn't include first name ID. This query is taking longer, and I'll be right back. I'm going to get a chair. There's a question. Let's see, I think I missed the gist of your question. So the question, are prob necessarily bad in general? Tell me more about what is necessarily bad in general. I think I missed a word, or I'm not sure what prob is short for, probably. Probes? Was it? Now I'm like, maybe it's probes. Yes. Okay. So are probes bad in general? Not necessarily in that context. So let's look at them again, and I'll show you. Probe residuals are often bad, but the probes themselves are not necessarily bad. Let's see if we have one in here, and we can discuss. So this query decided not to use. I mean, this query has on the new table. It has a very similar non-clustered index. The non-clustered index has in it report year, gender, and name count descending, but it doesn't have first name ID in it, and it's not sneaking in there. And so since it doesn't have it in there, SQL Server decided not to use it at all and said, oh, well, I'll just scan the clustered index of the table twice. Like, I'll just scan that twice. Wah, wah, wah. And oh, we're sorting everything in it too. That's fun, right? So this took 15 seconds. So when we index for windowing functions, covering the essential parts of the windowing functions really helps. So for fun, let's look at this index that it's asking for. It is asking for an index here. How many indexes is it asking for? It is only asking for 1. So when I expand missing indexes on the property, there's no 1, 2, 3. It's just 1. The index that it's asking for is this is what you will often see in the real world is indexes. The index feature will be like, I want an index and I want everything in it, right? I want another copy of the table. And it's not being real smart about this either, right? The only thing it's asking for in the key of the index is the join column. It's not even trying to optimize the windowing function. So when you see an index request like this, this is why we still have jobs, right? This is why the artificial intelligence is not yet taking over, because we do not have to give it this mammoth index that's a copy of the whole table. Not at all. We literally only need to add first name ID to that existing non-clustered index so that it has 4 columns instead of 3. This big index requests like this are a sign of, I need you to do the thinking for me and see if you can come up with a better index. That's really what these mean. So yeah, I don't want to give it that index. So to fix this, well, let me see in the plan. Before I move on, let's look. Here's the hash match. We do have an inner join in this one. Let's see what we've got on this plan. So on this one, we have a hash keys probe. So hash key probe in this context on this operator just means, so what it does in this, we're probing on first name ID. So the way the hash join works, this is the build phase. It will run first. So it builds an object in memory based on what it scanned from ref.firstname. And it does, even though we don't have a bitmap operator here, it actually is hashing the values for the first name. We're joining on first name ID, right? Yeah, that was the probe value. Yep, first name ID. So it is behind the scenes hashing those first name IDs into buckets just to compress them down and make them smaller. We don't see the bitmap probe operator here simply because it isn't doing an optimization with it down here. It only shows the bitmap probe if there's an extra optimization. The hash key probe, so the build phase goes first. We build one of the input tables, and then after that, the probe phase runs. And now let me just clean up my drawing. So build first, then probe. And when probe runs, it literally probes into the table using, so it hashed the values in one, it hashed the values in another, and then probe is just how it matches. It's how it does the join. Hash match, both of these inputs, they do not have to be sorted in the same way, right? They can be in different orders. The first name IDs don't have to be sorted, and it can still join them. So in this case, probe is not bad. It is literally just what is the thing that I'm doing the join on. The thing that can be bad actually doesn't show up in this one. Let's go back to the previous query and see that one. The thing that can be bad, it's not necessarily bad, is in the execution plan for this one. Takes a while for it to display all of it. Like I'm having it, part of the reason that this shows is 7 seconds here now that I think about it, we have CPU time of 4 seconds. It's often 3 for this one. We have a lapse time of 7.5. It's because I'm having Management Studio display all of these columns. This overhead will show up in elapsed, but not necessarily CPU time. So in this hash match, okay, so our hash keys probe is on first name, ID, gender, and report year. And then this probe residual can sometimes be a problem. So probe residual is going to be applied to every row that comes out of the join. So it does the probe first and like limits things down based on the first ID, report year, and gender. And then it's going to have to check every single row and do this residual operation on every row that comes out of there. So what is it doing on every row that comes out of there? It's checking, is the first name ID equal to, okay, so this is just a repeat, first name ID, gender, and report year. So this one, it's interesting because why does this show? It's the same columns as are in the probe. I think that it's reapplying these to avoid collisions in this case. So I think this one isn't a case where it's going to be problems. What sometimes will show up, and now my stuff is just artifacting. Also, it would only be applied to the 276 rows that come out of there. The probe residual, blah, 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 blah. Let's go back over to properties and actually, if the probe residual contains extra comparisons on different columns, those might be things that could be added to an index or optimized in a different way. But there are a lot of, that's why I'm like, there are a lot of cases where you look in the probe and you look in the residual and you're like, oh, this is just double checking essentially the same stuff because when it bucketizes things to do that comparison, it could have collisions, meaning two values bucketized to the same value. So then it has to double check, oh, did I have any false positives here? Is essentially, I believe that's what it's double checking in that case. But yeah, it's not that fun to look at. So the probe itself is not a problem. Sometimes the residual is a problem. I find that an I feel like I need a better answer to that though. So I think I need to look into that more. I need to look into more why do sometimes the same columns from the probe show up in the residual and sometimes they don't. That's the part that I'm not satisfied with in terms of like what's going on there, because it should be consistent. All right. So what we need to do to fix this on our new table, essentially what our index should be, instead of giving this the index that SQL Server has asked for, what I think we need to do is just explicitly add first name ID into our index. And now that I look at this, I actually want to do a test. So I'm going to do a test where adding include first name ID. I am going to now run this again, and I've modified it. The first version of this had first name ID as the key, and I'm like, okay, it's just being used as a join column here. I think it's actually going to do really well as an included column. Now, on this new surrogate table, the clustering key is just a column named ID. It is going to put the cluster, I mean, the actual definition of this will end up with that ID column right here. It will add that in, but first name ID is no longer in the key. So first name ID is going to stay as an included column. Let's go ahead and rename this. Now, the name I'm naming it to implies that first name ID is a key column. Please forgive me because that's now incorrect. And now I will look at the plan for the old table and the new table and see, have we gotten back our performance? And we have. The old table first name ID was secretly being added to the key of the index. I have made it added to the include of the index. It is not completely an identical index, but it can be used in the exact same way. And now we have the quote unquote fast plan back. So if let's go ahead and run these two. I'm going to run the first query first. The first query is not done. I was like 16 milliseconds, it's not done. The first query this time took, I am seeing a lot of variation here. We've seen it as fast as 3 seconds of CPU time. Now it's 4.4 seconds of CPU time. Let's do a second sample on query 1. I think a lot of it, yeah, this one was 3.4. It's just a little bit variable. It's just a little bit variable. And the second query that this used to take, what, 12 seconds? Now that we fixed the index, we didn't give it the whole covering index. We just gave it like the join column. We're at 4.6 seconds this time. Let's run it again. So there's probably a lot of variation in this one too. Oh, I ran this so that when I ran it again, I didn't have, let's turn them on. And then let's run the second query again and get another sample of that. And on our second run, we're at 2.8 seconds. So again, there's a lot of variation in this. We are down the logical reads is different. We've added an extra column to our table, and we are still doing a clustered index scan of the base table. This clustered index scan is in all the queries. It's when we join back and are picking up all of those extra report columns, it's deciding to do a clustered index scan. Now, if we want to tune this query and make it even faster, there's a couple different things we could do. If we have a query like this, so the thing with our query, if we're looking at our query, we are going to have to scan everything in the table, right? Because we are ranking everybody. And we're ranking everybody by name count descending. So I need to figure out, for a given combination of report year and gender, who has the highest name count. So one thing, I mean, we are going to have to read all the rows when we're doing this. We could try to do an index view. That might be an option in terms of grouping by report year and gender, and or doing the max. Well, we can't do max in an index view. So we could try to do something there. It's going to be a hard fit with it, but there is an easier fix that we could try that is a total hack, and this is the hack. So what I've done here is I have created a non-clustered column store index on the table that contains no data. This is just one of several hacks, and these hacks, by the way, what I'm talking about here is unsupported by Microsoft. If you do it and you have a problem with it and you open a ticket with them, they will just say, we do not support that. Sorry. But I present this to you because it is an option, and people know how to do it. So for example, Itzik Ben Ghan is the one who published this one. He also has published other, I call these batch mode hacks. So what we've done is we've created a non-clustered column store index with a filter on it. This is available in, so non-clustered column store indexes with filters. I'm wavering on whether it's 2016 or 2017 that we got that in. Feel like it might be 2016, but then I am like, maybe I'm wrong. I'm not sure. This came in, I didn't make a note here. Let's double check, because I have a blog post on this. So if we use search on SQL workbooks, batch mode hacks, I summarized all of these available hacks here. So this one is 2016 plus, which is when we got filtered non-clustered column store indexes. Got it. So 2016 plus. I have said only populate this column store index where first name ID equals 1 and it also equals 0. That can never happen. So you just put a filter in there that is impossible to meet, and this creates a column store index on the table that is destined to always be empty. When you insert rows, no rows can go in there because they don't meet the criteria. When you query the table, nothing will select to use the column store index because it's a useless column store index. But it does mean that if we run a query against the table, which table did I create it on? I created it on ref.firstname. So ref.firstname is joined to by both of these queries. Just having a column store index, even an empty column store index on the table, will allow operators in the query to use batch mode, and it can sometimes change the performance of the query. So let's take a look and see. We're at 10, 11 seconds here. This did not go in a positive way. Let's take a look at what happened. So one thing that happened is notice that we don't have segment and project operators anymore for our windowing function. A new operator has appeared in our plan that is a window aggregate operator. we can only ever get the window aggregate operator if we're using batch mode. Some operators are batch mode only. This is why this new 2019 feature of batch mode for row store is really good news, because it means if you're using windowing functions, you can get a better operator for them without having to use stupid hacks like this that are unsupported. Because you can only get a window aggregate operator if some table referenced in your query has a column store index on it, even if the column store index isn't used, which is a dumb rule. It's really weird. But anyway, it's sort of like a loophole is what we're exploiting here. So we did get the new window aggregate operator. That's really cool. But hey, wait a second. Why are we still slow? So we're still doing a clustered index scan here of the first name by year wide surrogate table, and we're scanning the whole table, and we are pushing it into a hash match inner join. Now, let's look at something in the plan here. In terms of the rows coming out of the window aggregate function, right? It's pretty good at estimating that. It knew that there is about 1.9 million rows, and this window aggregate operator is doing the ranking. How, who's ranked number 1, 2, 3, etc. But it's also ranking who's ranked number 576, who's ranked 67,242. When we get to the filter, that's where it says, hey, who's actually ranked number 1? If we look at how many rows are coming out of the filter, hey, there is an estimate problem here. We thought that there would be 1.9 million things ranked number 1. In actuality, there were only 276. Wah, wah, wah. So this means, because it thought a lot of rows were going to come out of here, it chose the wrong join. It chose it chose the right join based on the estimate, but in reality, for 276 things coming in here, wouldn't it be much nicer to just do a nested loop operator instead of a clustered index scan, especially for this large table? Yeah, I think it would be nicer. So to speed up this query, yeah, we actually have sped up the part of the query that uses our non-clustered index really well, and we even, well, it's running in row mode there, but the window aggregate operator, we even managed to get this guy to run into batch mode. But now what's slowing down our query is this part down here. And let's confirm that. If we ever want to confirm that, we can. In an actual plan, if we go to actual time statistics, so this hash match says elapsed time 142, but if we go down to this clustered index scan of this table, looking at the properties of that, yeah, that's where 10 seconds is coming from, is scanning that clustered index. So that is what we need to speed up now. Well, how do we speed that up? I'm actually going to go ahead and do this in a new, well, let's just paste it down here, right? So now we've got our batch mode hack going on in there. There's a couple different approaches we could take. We could, this one, updating statistics isn't going to help, because the thing that it's having a hard time estimating is how many of these are ranked number 1, right? We could put this into a temp table and make it into a 2-step query. That would help the estimates. Or we could do something riskier, and we could say, what are we going to do here? Inner nested or inner loop join is the hint. We could actually tell it, I want you to do a loop join, in which case we are now down to 828 milliseconds of CPU time, a little over a second of elapsed time. Even though we're showing all those columns, we have now forced this loop join here. Now, I'm not saying forcing joins is always a great idea. There's other hints you could do, or things like you could also use a temp table. But what I am saying is, even though what we've done here is a multi-step process. We indexed for this windowing function. And to index for a windowing function, you want to look at the partition by clause. You want to look at the order by clause. And then you want to ask, is there anything else that I'm joining to? Is there any other columns that are important to cover, especially if they're using the output of this, coming out of this CTE to join to somebody else? And in that case, it is first name ID. So the step 1 of speeding it up was just to get it to use the non-clustered index on the new table, which didn't, secretly sneak this column into the key. The second step we did speeding it up was to, and let's see how much of a difference this makes. I created an unsupported hack where I put an empty non-clustered column store index on the table. And that was specifically so that my query could use, oh, hang on, we aren't using it anymore. What the heck, SQL Server? Okay, so I've now said inner loop join here. Let's run this again and look at the plan. It decided not to use our new windowing function operator. That's interesting. Why? Right? I'm back to segment and sequence project. I'm in row mode for both of them. Row mode. Let's ref.firstName is still over here, right? Ref.firstName is where I created that empty non-clustered column store index. That's interesting. So if I don't have this join hint, and I do estimated plan, right? I do have window aggregate operator there. This is just going to be slow. That's interesting. So as soon as I hint that, I'm going to try a different hint and just see if it does the same thing. So what I'm doing here is I'm setting a row goal with option fast first, or option, what is it? It's fast one, I think. I'm setting a row goal with a fast option, which I do think is one of the funnier hints. And with this one, with a row goal, it essentially is saying, what I'm saying on this hint is just do whatever you need to do with the plan to get me one row back fast. I don't care how long the rest of the query takes, just get me one row back fast, which has the effect of lowering the row estimates for the whole query. Again, this can be a risky thing to do, but in this case, what I want to do is lower the estimate for the number of rows coming out of this filter. So this lowers that estimate to 1. When I do this row goal, similarly, it's deciding not to use the new batch operator windowing function. So I'm going to switch. Actually, I'm going to clean up stuff from my script. I am actually going to do, I have created so much stuff that I am just going to do a quick re-restore of the database while we go through the original slide. So just because I did go off script there, I am now going to just re-restore the database there. So what I'm doing right now is I am starting up. This script can take a little bit of time to run. It is the setup script for the final module. It is topic 9, indexing and untamed server setup. So if you're playing along, you may want to start this up as well. You can re-restore the database if you want using that setup script, which is 0 restore database, and then run it if you want. It just takes a little bit of time to run, so it's worth getting started on that. So looking at what happened with summarizing the stuff in the window function stuff. When we change things, if you do go in and change keys on an existing table, absolutely think about what was enforcing uniqueness on the old table and make sure that you're enforcing uniqueness on the same table. This is not only for data integrity, it can also help your query plans for SQL Server to know what combinations are unique. And in our case, queries are joining on those columns, so it's relevant. If you are thinking, if you need to enforce uniqueness in SQL Server, you have a lot of choices. You can use primary keys. So primary keys are one choice. They are backed by an index. So if you create a clustered primary key, it is the table itself and that the columns you specify in the key are enforcing a business rule. If you make it a non-clustered primary key, it's backed by a non-clustered index. Primary keys cannot have any included columns. Now, if it's a clustered primary key, it does have all the, it is the table. So it's not technically an included column, but yes, it is the table. So it sort of has included columns, but non-clustered indexes, no included columns on primary keys. You can create foreign keys against primary keys. If you're using replication, you have to have a primary key. It doesn't care if it's clustered or non-clustered. It just insists that you have a primary key. You can also enforce uniqueness on two similar but confusing things, a unique constraint or a unique index. And it kind of drives me crazy, the differences between these. Both of these are indexes. If you create a unique constraint, it will create an index behind the scenes. You can create foreign keys against it, just like a primary. All three of these things support foreign keys, with a little proviso on the third one. But the thing about a unique constraint that's a big bummer is that you are not allowed to put included columns on it. Whereas if you just use a unique index, which is, both of these are indexes, but if you unique index, just different syntax, right? You can use included columns. When you create a unique index, the uniqueness is only applied to what you put in the key of the unique index. And unique indexes are non-clustered indexes by definition. You can't create a unique, well, you can create a this text should say unique non-clustered. You can create a unique clustered index. It's just a clustered index. So let's actually just change this heading and say unique non-clustered index, right? Because you cannot put a included column in a clustered index. That's not possible. So with a unique non-clustered index, you can add included columns. It doesn't affect the uniqueness, right? The uniqueness just goes against the clustering keys there. So why would I create a unique constraint ever? Right? Because if I'm creating an index and I'm going to have the overhead of dealing with it for inserts, updates, and deletes, why wouldn't I want the option to use included columns? Well, the main rule is that a constraint is technically a business rule and an index is not. So some people want to use unique constraints simply because they are constraints. And there is actually a practical aspect to this in a way. When DBAs are going around the system and they're looking for indexes that aren't used, indexes that don't have a lot of reads to them, but may have had a lot of writes to them, a DBA might accidentally drop a unique non-clustered index if it isn't actively being read. Now, hopefully they see that it's unique and realize that it's enforcing a business rule, but it's possible that they can miss it. So if you're worried about that, a constraint maybe makes more sense, but I think it's kind of like an edge condition. Like if your DBAs may be dropping unique indexes, you've probably got other problems too. Not that it's something that I couldn't do. I could totally do that. I could totally do that as well. All right. So in terms of changing clustered indexes, we always want to test queries for regression if we are changing those indexes. If you do have Query Store, if you're on SQL Server 2016 or higher, as we're going to see in the next session, Query Store can really help you capture queries and measure performance. Third-party monitoring tools can also be great for this. When it comes to measuring windowing functions, Itzhak Ben-Gan came up with a great acronym for this. You want to index the partitioning part of the windowing function. That's the part that does the grouping. You want to index the ordering part of the windowing function, and then the coverage part, that's the part that was first name ID that covers the joins. So indexing this part, the coverage, this is what we join on later. Don't miss those parts of it as well. So that is what to take away from this one.